So let's go ahead and get started then. So before we actually get started, does anyone have any quick questions on tonight's homework? Okay. So a few quick announcements before we get started. So quiz 4 is going to be next Monday from 9 a.m. to next Tuesday at 9 a.m. So that's your 24-hour window. Covers lessons 11 and 12. And so the other thing is that I also have a survey that is sent out on Monday, and because I want to try and focus on trying to find ways to improve the lectures, I would like it to be due tomorrow at noon. And I noticed a good chunk of you in this section have looked at the survey and taken it, so I have peeked at what you guys wrote, and I kind of am taking that into account now. So one of the things I would like to encourage a little bit more is, like, I'm trying to encourage throughout the lectures, is idea of student involvement, because when I help you, when I ask you guys questions and ask certain people like what do they get on this particular problem, it's not me trying to like shame you or judge you or ridicule you if you're wrong. It's more like I'm just trying to help you out, guide you to the right answer and whatnot. So it's more trying to help you guys out. So that's part of the reason why I ask you guys a lot of questions. So yeah, don't take that to me. I'm like trying to like put you on the spot and shame you if you're wrong. It's not that at all. Just trying to help you guys out, understanding the concepts. So okay. So with that being the case, let's go ahead and take a look at the warm-up. So for those of you that did the warm-up, what did you get as your answer for your derivative? And for those of you watching online, you can go ahead and take a second to pause the video if you need to, so you can take a second to do the warm-up. Okay. So for those that did the warm-up, what did you get as your derivative? Give you guys a second to look at it then. Another minute. So raise your hand if you got what did you get as your derivative? So maybe let's take a step back. So in this case, what would help is that this is the same thing as 9 times secant of x raised to the power 4, right? So in this case, it seems like we're going to need to apply chain rule here. So let's first identify our inner function and our outer function here. Okay. So what would our inner function do here? Yeah. Not almost, but not quite. So it will involve secant, but for now I think it would be better if we just focus on just secant, because we do know the derivative. So we have secant of x, so in that way the outer function will be 9x to the 4th. So x to the 4th. So that way g prime of x, does anyone remember what that is? Yep, secant of x times tangent of x. And then, well, f prime is just a quick application of power rule, so that's just 36x cubed. And then so as a result, that tells us f prime of g of x then becomes what? 36 times what? Secant cubed, good. Of x. So, as a result, if we multiply these two things together, the red and green parts, because those are what we need for a chain rule, that tells us that y prime then becomes, well, 36 times secant cubed of x times secant of x times tangent of x. So that tells us that this is just 36 times, secant to the fourth, because we have we have a secant cubed and a secant here. So secant to the fourth of x times tangent of x. So that is going to be our derivative here. All right. So any questions on that? Okay. So for now, we will need this a little bit later in the lesson, but for now, let's just go ahead and leave it as is. So what we're going to do now is we're going to focus on more chain rule, but more specifically, this lesson is supposed to be sort of an amalgamation, in a sense, of all the rules that we've covered so far. So in this case, not only are we going to need chain rule, but we're also going to need to bring in product and quotient rule as well, because in this case, we'll be dealing with functions that need usually one or two, or usually need two of those at one time. So let's look at the derivative rules we need for today. So we have f of x plus or minus g of x. Take the derivative of that. That's just f prime of x plus or minus g prime of x. Okay. And then we have f of x times g of x prime. That's just, well, f prime of x times g of x plus f of x times g prime of x. And then, so this is just product rule. So then f of x divided by g of x, derivative of that is just, well, low d high. So g of x times f prime of x minus high d low. So f of x times g prime of x. And then all over low squared. So g of x quantity squared. Okay, there we go. Okay. So that's quotient rule. And then last one that we already talked about on Monday was the chain rule, which says that the derivative of a composition of functions, f of g of x, is just f prime of g of x times g prime of x. Okay. So, as I mentioned, this part here is just product rule. This is just quotient rule. And this is just chain rule. Okay. So we're also going to need one more derivative rule. So in this case, as you might have guessed, it's going to be the derivative of the natural log function, because, well, part of the title of today's lesson is exactly that. So here's what the derivative of natural log is. It is, wait for it, 1 over x. That's it. It's literally just 1 over x. Just take whatever's inside your natural log and just take it 1 over that. So, all right. Okay. So another thing that you might have noticed is that because we're going to be using the natural log function quite a bit, we should also recall some of the important properties of said function. So let's do that now. So we have, well, let's see, first function, or the first property rather, is natural log of a times b. So this is just natural log of a plus natural log of b, if you recall. And then the second thing we need to remember is natural log of a divided by b, which is just natural log of a minus natural log of b. And then the third thing is natural log of a raised to the power of b is b times natural log of a. And then the last thing is natural log of e to the x is equal to x. Now, at this point, you're probably thinking, well, it's good that we have these properties from pre-calculus, but why do we need them? Like, why should we care? Well, the thing is that technically speaking, you don't need them, but it's strongly recommended you use them. And here's why. So if we take a look at this property, what you'll notice is that if we have a product of two functions, that allows us to split it up as this. So this will give us less product rule. Okay. So that in a similar fashion, if we take a look at this second property, that will give us less of which rule? Less quotient rule. Good. Less quotient rule for property 2. And then the third one is going to help us out because this will actually give us less chain rule. Okay. So that's all I wanted to say on that. So any questions on that before we get to example 1? Okay. So let's take a look at this. So if we take a look at this function, natural log of x squared times e to the x, there's sort of two ways we can differentiate this. So the first way is just take the derivative, or take the function at face value and just differentiate it as such. So method 1. So differentiate it as written. Okay. So in this case, what you'll notice is that if you look at this function, what we ultimately have is one function of x inside another function of x. So because of that, it looks like we're going to need chain rule here. So one function inside another. So need chain rule. Because in this case, you can think of this one function inside another thing as sort of the quote-unquote biggest thing happening here with y. So biggest thing here with y. Okay? So in this case, let's go ahead and use g of x and f of x as in chain rule. So in this case, this is our inner function, g of x. And our outer function is f of x. Okay? So what would our inner and outer functions equal here? So let's start with the inner function. What would that be?
Would it be x squared times e.
Bingo. Good. And then the outer function as a result?
Just out on the right.
Yep, it's natural log of x. Good. So, like I said, in this case, f of x, g of x are as in chain rule. Okay. So the nice thing is that, as we just established, well, we already have what f prime of x is, as we just looked at. So f prime of x, well, that's just 1 over x. And so as a result, well, that gives us f prime of g of x, because all we have to do is just replace x here with whatever g of x is. So in this case, that's just 1 over x squared times e to the x. So that's the first part of the chain rule we'll need here. But what about g prime of x, though? So what you'll notice is that we have x squared times e to the x. So we have two functions of x being multiplied together here. So what rule do you think we'll need here? Product rule. So we're going to need to use product rule to find g prime. So product rule. Okay? So if you use product rule to find g prime, what do you end up with? Go ahead.
X squared, x squared times e to the x plus 2x times e to the x.
Good. So we have the first function times derivative of the second, so just e to the x. And then plus derivative of the first function, 2x, times the original second. So e to the x. Good. So, now that we have all that, let's see, that'll give us what? So, y prime is equal to 1 over x squared times e to the x times g prime of x, which is x squared e to the x plus 2x e to the x. Okay? So we have that, which is good. So I'm going to rewrite this a little bit differently. So we have, if we put this on the numerator, this g prime of x on the numerator here, then what we get is that I'm going to write this as 2 times x times e to the x plus x squared e to the x. And then all over x squared e to the x. Okay? So even though these two are the same, I'm just rewriting this slightly differently, and you'll see why in a second. So what you'll notice is that, well, these two expressions on the numerator both share the common denominator of x squared e to the x. So let's go ahead and split this up. So we have 2x e to the x over x squared e to the x, and then plus, well, x squared e to the x over x squared e to the x. Okay? So what you notice from this is that, well, wait a minute. We have the exact same thing on top and bottom for the second term, so the second term just becomes 1. So no questions asked there. But then for the first term, the e to the x's cancel each other out, but then only one factor of x goes away on top and bottom. So here you ultimately end up with 2 over x. So that will be your derivative in this case. So any questions on that?
So we didn't have to use any of the natural logs for this one?
Not for this method, no. But actually, that's where the second method comes into play. So method 2 is, as you mentioned, just use log rules first. So if we do that, we say, okay, don't worry about differentiating just yet. Let's just break this up as much as we can before differentiating. So if we take this expression here and use the log properties that we have up here and break it up as much as we can, how can we break this up?
You can do the natural log of x squared plus the natural log of e to the x.
Yep. Natural log of x squared plus natural log of e to the x. Good. So then what can you do with these two terms?
You could make the natural log of e to the x just e.
E?
Oh, x.
X. Okay. So that's the second term. What about the first?
You could do 2 times the natural log of x.
Right. So 2 times natural log of x, just throw this power out here. And then e to the x, or natural log of e to the x just becomes x. So then you'll notice this is much easier to differentiate, right? Because, well, y prime then becomes, well, derivative of 2 times natural log is just 2 over x, and then plus quick application of power rule is just 1. Okay. So any questions on that? Okay. So now let's do another example with natural log, but with a function that's a little bit crazy. So now let's go ahead and differentiate natural log of the square root of 5x plus 1 divided by x squared plus 4. So based on the two methods that we just did, one where we just differentiate this as written or use log rules first, which of the two would you prefer to do in this case? Okay, how about we do a quick show of hands? Who wants to do method 1 first? Who wants to do method 2 first? Good, so do I, because that's the only thing I have written in my notes. So we're doing that. So doing that, so let's see. Let me write that down. So could apply method 1. Could being the operative word, but finding the derivative of the square root of that, I don't want to do that, and I'm pretty sure you don't either, gets messy, or at least in this context if there's a more optimal option. So log rules first. Okay. All right. So, yeah, okay. So, let's go ahead and start by breaking up y as much as we can here. So we have the square root of, natural log of the square root of 5x plus 1 over x squared minus 4. So, if we want to start breaking this up as much as humanly possible here, what's the first thing we can do? So we have square root, so what can we do with that?
Just square the whole function.
Not square the whole function, because remember, this is the same thing as...
Could you make it to the power of the half?
Exactly. So then you can throw that half outside as we did before, right? So we have 1/2 times natural log of 5x plus 1 over x squared minus 4. So that takes care of that. So then that equals, let's see, what's the next thing we can do? So we notice we have one function of x divided by another function. So it seems like we could just use the rule where we can split it up as a difference. So we have 1/2 times natural log of 5x plus 1 minus 1/2 times natural log of x squared minus 4. So that's that part, but then what do you notice from this? So what you notice is that, well, x squared minus 4, that by itself has a nice factorization to it, doesn't it? So we have x squared minus 4 is the product of what two factors?
X plus 2 and x minus 2.
Bingo. Yep, 2 plus 2 and minus 2. Well, minus 2 plus 2. Okay, so taking that into account, what does that tell us about how we can break this up further? So we have 1/2 times natural log of 5x minus 1, nothing we can do past this, and then minus 1/2 times natural log of what? So if we use this factorization here, we can split this up further as what? So if we use this factorization, this is the same thing, just focusing on this, this is the same thing as natural log of x minus 2 times x plus 2, right? So if we were to use if we were to use the appropriate natural log property, what would this simplify to? Or what would this be broken up as?
Would it be the natural log of x minus 2 plus the natural log of x plus 2?
Yep. So we have 1/2 times natural log of x minus 2 plus natural log of x plus 2. So we have, as a result, we have, if we distribute the 1/2 into this expression, we have, ultimately, we have 1/2 times natural log of 5x plus 1, and then minus 1/2 times natural log of x minus 2, and then plus 1/2 times, minus 1/2 of natural log of x plus 2. Okay? So in terms of the way we can split this up as much as possible, this is the best we can do. So this will be the way we need to differentiate the function here. Okay? So now let's go ahead and differentiate this. So y prime is then what? So let's focus on this first term here. So we have 1/2 times what? So let's go ahead and do the chain rule on this. So if we focus on just this and we wish to differentiate it, well, we first need to identify the inner and outer functions, right? So the inner function will be what here?
Five
5x plus 1. And then as a result, the outer function will be natural log of x. Okay? So then as a result, g prime of x, as a quick application of power rule, is just 5. And then f prime of x is just 1 over x. So then as a result, f prime of g of x then becomes, well, just replace x here with g of x. So we get 1 over 5x plus 1. Okay? So then as a result, that should tell you that the derivative of natural log of 5x plus 1 is then just 1 over 5x plus 1 times 5. So we have 1 over 5x plus 1 times 5. So that's the first part. So then if we do a similar thing with natural log of x minus 2, what would our derivative of that be? Yep, 1 over x minus 2. And then if you want to be consistent with chain rule here, you can just multiply this by 1 because that's the derivative of x minus 2. And then similarly, the derivative of natural log of x plus 2 is just 1 over x plus 2 times 1. Okay? So then as a result, that tells you that the derivative ultimately becomes the following. So we have 5 over 2 times 5x plus 1 minus 1 over 2 times x minus 2 minus 1/2 times x plus 2. So that will be your derivative in this case. So that is example 2. Question?
Is it supposed to be plus 1 over 2?
We're at?
The second number. So at the solution,
Yeah.
so it's, you say minus 1 over 2 times x plus 2. Is it supposed to be plus instead of minus?
Oh, here?
Yeah.
No, because remember, we had natural log of x squared plus 4 is equal to this whole thing, right?
Yeah.
So then here what we did was we distributed the negative 1/2 to both terms here.
Okay.
So that's how we get the negative here. Okay. So any other questions on that? Alright. So that's all I really wanted to say on the natural log stuff. So now let's go ahead and deal with some slightly more complicated functions that don't involve natural log. So now in this case we're asked to differentiate e to the 6x squared times cosine of 9x. So in this case what you notice is that we have two functions of x being multiplied together is sort of the biggest thing happening here. So biggest thing here is a product of two functions of x So if that's the case, that should tell you that the sort of the biggest rule that we need to apply here is So need product rule if we wish to differentiate this. Okay. So in this case, what we're going to do here is say, all right, let's let our f and g be as in the product rule now. So we have f of x and g of x. So in this case, like I said, so let's f of x, g of x be as in product rule. Okay. So if that's the case, that should pretty quickly tell you that the two functions f and g in this case will be e to the 6x squared and cosine of 9x. All right. So in this case, since we need to use the product rule here, we are going to need just the corresponding derivatives of f and g. We don't need to worry about compositions in this, well, we don't need to worry about compositions of f and g in this case. However, f and g both have compositions of functions in and of themselves. So in this case, to find f prime and g prime, you're going to need chain rule for both of them. So use chain rule to get these. Okay. So let's start with a slightly simpler one. So let's focus on what the derivative of cosine of 9x is. So if that's the case, then if we have cosine of 9x, then its derivative becomes what?
Negative sine of
Yep. Because in this case, well, we have negative sine of 9x. That will be your, in this case, your f prime of g in this case. Well, the derivative of the inner function, well, that's just 9. So ultimately, you have negative 9 times sine of 9x. Okay. So that's the derivative of g. Now let's use similar reasoning to get the derivative of f. So somebody else, what would the derivative of f equal here? Go ahead.
12x times e to the 6x squared.
Yep. So e to the 6x squared times, in this case, derivative of the inner function, so 12x. So you have 12x e to the 6x squared as you have. Okay. So in this case, these would be your corresponding derivatives. So now let's go ahead and plug that all into our good old product rule. Okay. So if that's the case, then that says, all right, well, y prime becomes, well, f times g prime. So we have e to the 6x squared times negative 9 times sine of 9x. And then plus g times f prime. So that would just be cosine of 9x times 12x e to the 6x squared. So if we clean that up a little bit, you should end up with negative 9 e to the 6x squared times sine of 9x plus, well, 12x e to the 6x squared times cosine of 9x. Okay. And that will be your derivative in this case. So, any questions on example 3? All right. Give you guys a second to write that. You write that down. So then I'll put example 4 on the projector so you guys can take a second to look at that. So we have, for example 4, the position in meters of a particle moving along a straight line is given by S of t equals 5t divided by t squared plus 7 raised to the power of 3. And t is in seconds. So in this case, we're asked to find the velocity at time t equals 2. And we have to round our answer to 4 decimal places. So here's the thing. Before we formally start the calculations here, in this case, if we want velocity and we're given the position function, can anyone remind me of the relationship between position and velocity in this case?
Velocity is the derivative of position.
Right. So recall, v of t equals s prime of t. So that means we got to find s prime of t. Okay. So if that's the case, well, that means we need to find our derivative of this quotient here. But then, in this case, since the biggest thing here is a quotient, so ultimately, we're going to need to use which rule here? If the biggest thing happening here is a quotient. Quotient rule, good. The aptly named quotient rule. How convenient. Okay. Okay, so if that's the case, now we're going to let f and g in this case then be as in quotient rule. So we have f of t and g of t, because, well, t is our input variable here. So then in this case, we let f and g be as in quotient rule. Okay. So in this case, if you recall, well, f corresponds to the numerator and g the denominator. So we have 5t is f of t, and g of t is the t squared plus 7 quantity cubed. All right. So the good news is that in this case we just need f prime and g prime again. So f prime, well, that's pretty nice and straightforward. It's just 5. Just quick application of power rule. But then what about g prime? In this case, we have one function of t inside another. So if we use chain rule, we should end up with what as our derivative here? Go ahead.
3 times t squared plus 7 times 2t.
Exactly, right. So in this case, we have 3 times t squared plus 7, quantity squared. So in this case, that would be the derivative of the outer with composition with the inner function. And then 2t would be the derivative of the inner function. So clean that up a bit to get 6t times t squared plus 7 quantity squared. Okay. So now that we have the top and bottom and their corresponding derivatives, let's go ahead and plug that into our good old quotient rule. So we have v of t equals s prime of t. So in this case, we need low d high. So we have t squared plus 7 quantity cubed times 5. And then minus high d low. So we have 5t times 6t times t squared plus 7 quantity squared. And then all that divided by g squared. So we have t squared plus 7 quantity cubed. All that squared. Okay? So now let's go ahead and clean this up a bit. So on the numerator, we have, well, 5 times t squared plus 7 quantity cubed. And then minus, well, best thing we can do is just multiply 5t and 6t. So we have 30t squared times t squared plus 7 raised to the power of 2. And all that divided by t squared plus 7 raised to what power? So we have t squared plus 7 to the power of 3, but then we also have that raised to the power of 2. So that becomes what power ultimately? Yeah, just 6, right? Because in this case, you just multiply the two powers here, and that would be your answer. Okay? But here's something you might notice. So on the top, looks like we have two factors of t squared plus 7 on both terms. And it looks like we also have several factors of t squared plus 7 on the denominator as well. So if we cancel out all the unnecessary factors of t squared plus 7, looks like we can clean this up a little bit more. So if we do that, then what would the numerator become as a result?
Minus 30 t squared.
Yep. So yeah, 5 times t, what was it?
Is it 5 minus 30 t squared?
Not quite, because we have 3 factors of t squared plus 7, but we only have 2 on the second term. Yep.
Would it be 5 times the quantity of t squared plus 7 then minus 30 t squared?
Right. And then on the denominator, we have t squared plus 7 raised to the what power? Good. Okay. So at that point, we can say, all right, you can leave it as this, or if you want to clean this up, this numerator up a little bit more, you can rewrite this as negative 25 t squared plus 35. And then over the same denominator, t squared plus 7 raised to the power 4. Okay. So this would be our derivative. That would be our velocity function. But oh, wait a minute. We still need to find the velocity at time t equals 2. So just let t equal 2 in our derivative. So we have v of 2 is equal to what? So we have negative 25 times, well, 2 squared, so just 4, and then plus 35, and then divided by, well, t squared, so 2 squared, so 4, plus 7 raised to the power 4. Okay. So in this case, since we actually do have to round your answer to 4 decimal places, if you put this into a calculator, then what do you get as your approximated answer here? If you plug this into a calculator. Exactly. Yep. It's equal to negative 0.0044. And then, of course, meters per second, because that's our units in this case. So that would be your answer here. Okay. So any questions on example 4? Okay. So now let's take a look at example 5. Sort of, in this case, now we're coming back full circle to our warm-up problem. So in this case, we're asked to differentiate y equals 9 times secant to the 4th of 2x cubed minus 5. So sort of taking motivation from all the examples that we've been doing up until this point, let's take a look at what the biggest thing here is. So biggest, quote unquote, thing here. So what would be the biggest thing happening here? In this case, we don't really have a product or a quotient here, so yeah. Yeah. Well, I thought you had a hand up.
No.
Okay. So which of the three rules do we ultimately need to use here? Chain rule. Because in this case, the biggest thing happening here is one function inside another. So, need chain rule. Okay. So here, we say, all right, well, let's let g of x and f of x be as in chain rule. Okay. Make sure we're color coding correctly. So let's f g be as in chain rule. Okay. So g of x, like I said, that's the inner function. And outer function is outer f of x. So first off, what would you choose as your inner function here? What would you want to choose as the inner function in this particular case?
Would the inner function be the secant of 2x cubed minus 5?
So you could do that. So funny story about that actually. So the thing is, when I taught this class last fall, like when I taught this class before, I sort of had the warm-up structured so that way that would be the correct inner function, so that way we would be consistent with the warm-up. But then both of my sections then said, oh, just use the cubic. So I was like, okay, well, then I'm going to change the warm-up now, so that way we'll have the inner function be the cubic. But now you guys are saying, oh, let's have it be the secant of the cubic. I'm like, oh, well, this just feels awkward now. So I guess what we'll do, just for consistency with the warm-up, is we'll just let g of x be 2x cubed minus 5. You can use secant if you want, but I'm just going to use the cubic here just to be consistent with the warm-up. Because what you'll notice is that if we do that, then our outer function then becomes 9 times secant to the 4th of x. But, oh wait a minute, we already know the derivative of this, don't we? That was exactly the warm-up. So, g prime of x, well, that's just a quick application of power rule, so 6x squared. And then, in this case, well, the derivative of this, of f prime, or just f, so if we take the derivative of f, well, we already did this in the warm-up. So f prime of x then becomes, well, 36 secant to the 4th of x times tangent of x. Okay? So as a result, well, f prime of g of x then becomes, well, 36 times the secant to the 4th of 2x cubed minus 5 times tangent of 2x cubed minus 5. Okay? So as a result, if we multiply these two together, we end up with y prime equals, well, 36 times secant to the 4th, 2x cubed minus 5 times tangent of 2x cubed minus 5 times 6x squared, which is then equal to, if you combine these two constants together, you have 216x squared times secant to the 4th of 2x cubed minus 5 times tangent of 2x cubed minus 5. Okay. And so what this example tells us is that there could be cases where you need to apply chain rule multiple times in a problem. So may need chain rule more than once.